Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Gary Ahn, who is a professor of surgery and vice chair of surgical research at the University of Vermont. He specializes in trauma and surgical critical care. His research interests include computational biology, mathematical modeling, and computer simulation, as well as translational systems biology. Welcome, Gary.
Thank you very much for having me on.
Absolutely. So I want to use one of your older papers to set up the context and the background, and it's called In Silico Experiments of Existing and Hypothetical Cytokine-Directed Clinical Trials Using Agent-Based Modeling, in which you say the objective is to introduce a form of mathematical modeling called agent-based modeling, ABM, and demonstrate its potential uses in the evaluation of the dynamics of the innate immune response, IIR, and the development of possible treatments for systemic inflammatory response syndrome, SIRS, or multiple organ failure. And so before we get into the details of this, Gary, what exactly is ABM, and what is the motivation of getting into ABM in this kind of
Yeah,
problem?
sure. I can talk about that a little bit. So agent-based modeling is a form of computational modeling that looks at systems as aggregates of interacting components that operate based on a series of rules. It is, related to, more formal computer science objects like cellular automata. But agent-based modeling, it matches very well with how many of us see the world as working. So when you look at a system that has multiple components, you can have individual components interacting with each other given some sort of radius of information transfer, and then they act upon a series of rules based on that, and then the overall dynamics of the system arises out of those sets of interactions. So many people interact with agent-based models or have experience with agent-based models by going to the movies when people did go to the movies. So these very large like battle scenes or crowd scenes that are under computer-generated imaging are in fact agent-based models. So one of the first examples was from the Lord of the Rings movies, where you can imagine that the battlefield represents this giant checkerboard, and each individual creature represented in that particular battle is a standalone little computer program that has relatively simplistic stand and fight rules. And when the armies meet each other, then the individual agents undergo engagement and they follow their rules, and then you get this kind of very biomorphic type of behavior. Now, one of the characteristics of agent-based modeling is that it produces paradoxical behaviors where you can't necessarily infer the behavior of the overall system based on the behavior of individual rules. So like in the the CGI example, when they first did these simulations, they could not actually get the armies to fight. They would program what they thought were very reasonable standard fight rules, but once you had populations interacting, it manifested this exploit where the armies would retreat almost immediately upon contact. So one of the benefits of this type of modeling is where you can have what you think are relatively confident ideas about how individuals behave, but when you take them into aggregate, you get these population effects that that result in counterintuitive and paradoxical behavior.
So if I understand this correctly, Gary, if I have a set of heuristics or set of rules, and each of those rules by itself is sort of simplistic. So both objective function that agent might want to minimize or maximize, or the rules that agent might want to operate under, are relatively simple. And then are you assembling then a group of those types of agents? And there might be interrelationships between them, but each of them could be defined more simplistically, and then you're looking at what the net effect might be at the system level.
That's exactly the issue. And I think one of the benefits of this type of modeling is sometimes you can look at those, rules of how individuals behave. And you can make an inference on how the system would behave as an aggregation of those agents. It turns out, however, that the interaction networks are very important in determining how that overall system behaves, and you can't necessarily assume that you can understand how the overall system functions based on how individual rules occur.
Yeah, so this is very amenable to biological systems, and that is where you focus on. And presumably, when we look at a complex biological system, we can look at the components of that system. And the components are probably more easily definable, but often both from a kind of pharmaceutical perspective as well as other type of intervention perspective, the net effect of a set of actions is often very, very difficult to define prescriptively, right? So is that the idea that you can define the biological agents, different categories of them, define them more simplistically, and then step back and see how, if you turn them all on, what the net effect is going to be in the biological system?
Yeah, that's very close to what the intent is. So, the traditional reductionist method of biomedical research, which is to take a system and reduce it into experimentally investigatable parts, right? That is kind of what the tradition of biology is you look at tissues, and then you look at cells, and then genes, et cetera. There's this kind of taking apart process in order to get, let's call them linearly reducible questions that can be answered with an experiment. And basically the sum total of almost the entire sum total of mechanistic information we have about how biology works is a result of, the successes of cellular and molecular biology. So as it turns out, the vast amount of knowledge about how these systems work is characterized in sets of rules about how cells behave or molecules behave or genes behave under certain types of conditions. And so I think that is, part of the challenge associated with this reconstructive property or paradoxical behavior when you're dealing with populations of these entities. So for instance, I'm sorry.
Yeah.
So if you're talking about a traditional drug development pipeline, you have a punitive target, you investigate that target in a series of in vitro experiments, cell cultures, and you basically scale up till, you get to preclinical animal trials, and then you try them in humans. Well, each one of those translational steps is a very, very lossy process. You have to make a whole series of inferences. And, it turns out in general that, given the failure rate of most, drug candidate molecules, the failure rate is extraordinarily high. So there's this I call it the reverse Humpty Dumpty effect, where the standard, process of doing biomedical research is to take a system apart into its component pieces, but you can't kind of put those pieces back together in a way that captures the richness of the original system. And agent-based modeling is a way to do that within a computer simulation.
Right. Yeah, that's very interesting. So these types of issues actually exist in financial markets, in organizations, complex organizations. I was at Pfizer in the 90s, and pharma R&D, as you described, has this problem, right? So we have a variety of functions in the organization: clinical, manufacturing, toxicology, a variety of other functions. They all have sort of prescriptive objective functions that they're trying to minimize or maximize. And ultimately, when we think about the R&D process as a complex set of things that need to integrate different things together, we don't really have a good idea of how those things are going to interact with each other. And so it's a similar situation, right? So we don't really have ex-ante expectation of what the behavior is going to be. We know a bunch of components there that we can understand, but we don't really know the interactions between the components, or any kind of complex other behavior that might emerge, right, in the system because of those components. And so I want to jump into one of the other papers here to make it very practical. And it's entitled "Examining the Controllability of Sepsis Using Genetic Algorithms on the Agent-Based Model of Systemic Inflammation." You want to talk a bit about that paper and what the objective was, and how you applied ABM there?
So, to step back just very briefly, that original paper that you described, which I think is from 2004, was essentially a proof of concept showing that if you took essentially the state of knowledge that was present in the critical care community in the late 1990s about how things actually work, and you instantiated that knowledge within an agent-based model, it essentially makes that knowledge map go. It makes that static diagram of interactions into a movie. If you had such an object and you had tested the anti-cytokine trials that ultimately failed in the late 1990s, you would have seen that they would have failed, right? So the idea is that you were using the computational representation of knowledge as essentially a filtering mechanism to identify what will not work.
Right. It's just too simplistic a representation.
Well, which part is too simplistic representation?
Whatever we do in the clinical trials or any kind of R&D process, I guess our natural tendency would be to sort of reduce the complexity, right, and make it more understandable and more usable. But in the process, you actually use a lot of the rich characteristics.
And you're making a whole series of essentially opaque inferences, right? The supposition is that a rat or a pig under tightly controlled experimental conditions somehow reflects the clinical problem. I think that is an issue. So this model, the idea of using an agent-based model for an in silico trial is essentially a hypothesis verification object task, right? Because there is no opacity for the computational model. It only includes what you put into it. It doesn't have any sort of hidden features, and therefore that computational object represents a pretty objective representation of how you believe something works. Now, so the model, the in silico trial, gives your hypothesis the benefit of the doubt. It's like, okay, there's no hidden features, there's no inefficacy of the drug, in terms of biodelivery, there's no protocol divergence or whatever, right? You were saying you believe the system works in this particular fashion. You believe that interdicting that system in this particular way will work. This will see whether or not it works, and it doesn't work. So so at that point in time, the result was kind of a negative one, meaning that you can't say what's going to work, but you can say what's not going to work. So it took 10 plus years before I figured out a way to identify what actually would work. And that is the second paper you referred to, the use of genetic algorithms, which is a computational method, essentially uses evolutionary principles for an optimization task. So what we did was we took the old model that had been demonstrated to disprove the efficacy of mediator-based therapies for sepsis, of which there are none. And
sepsis is just sort of a very high inflammatory response and a very high mortality rate too, right? So people are pretty sick when they are.
Yeah, they are. This is another issue with sepsis, is that the definition of sepsis varies, and it's very heterogeneous, and it's very let's call it consensus or political based. It's not terribly biologically based, and I've written about that as well. But suffice it to say that it is essentially what people who are in the intensive care unit die from. It is received more recent notice because cytokine storm associated with COVID is a sepsis-like condition. It's basically disordered acute systemic inflammation. All right. So the idea then was, now we have this computational object, and can we use it as a proxy system to investigate whether or not it can actually be controlled in a prospective fashion? So I'm gonna refer back to a paper that's not one of mine, but some that you might be interested in, and when your readers would be interested in, which is called "Can a Neuroscientist Understand a Microprocessor?" And it's a variant of this old paper from, I think, 20 years ago that asked whether or not biologists can understand a radio. And basically it is a example of whether or not the tools that are used in biology can actually gain any sort of meaningful information about the system you're trying to study. I'm talking about it in this particular context because that paper uses a microprocessor, a ground truth object, to test the methodology that's being used in biology. And that's what the agent-based model in this particular circumstance is being used for.
So the genetic algorithm here, again, you sort of described the trial and error process. So you have a hypothesis, you can test it, you can figure out if it most likely doesn't work. So you have set of hypotheses that don't appear to work, but is a genetic algorithm there is really kind of feeding that those results of those experiments and really let it evolve into something a little better?
Not exactly. In this particular circumstance, the thing that's not being optimized is not the hypothesis underlying the agent-based model. There's other research working on that.
Yeah.
Rather, it is the idea of trying to find a set of multimodal and temporally variable therapies that might work. So let me expand on that just a little bit. So people may have heard about precision medicine or personalized medicine. It's used primarily in the context of cancer. But the idea in terms of sepsis is one of the stated challenges of doing clinical trials in sepsis is the complete heterogeneity of the sepsis population. And drugs may not work because patients are different from each other or different from themselves at different times in their time course, and the idea of a one-size-fits-all therapeutic intervention will not work. And the logistics of doing combinatorial therapeutics, particularly those that are going to vary over time, is just not tractable in the clinical setting.
You don't have time
well,
also.
you don't. I mean, you can't actually figure out how to do that, because let's say that you had 4 different drugs you might have to give in 4 different combinations every 12 hours, and you had to figure out how does that actually work. That's a multi-dimensional optimization problem, which cannot be done in the real world, but that's exactly what genetic algorithms are for. So this particular paper said, okay, we're just going to determine whether or not this particular system can be controlled, and therefore we will construct a genetic algorithm focused on optimizing cytokine manipulation of the model for every 12 hours for the first 7 to 14 days, and see whether or not you can actually affect the mortality of a high mortality cohort.
Is it personalized for an individual, or is it
well?
not
So the
generalizable?
GA presents a generalizable, multifactorial, and multidimensional intervention that works for the largest group possible. So in this particular circumstance, it takes essentially, I think it was a 80% mortality cohort and drop that mortality rate to 10%. Now that's a static policy. That's a consistent policy that requires manipulating 12 cytokines in different directions every 12 hours. But that is applied lockstep. To get personalized, you need to do adaptive therapy, and that requires the application of a particular control policy at a particular configuration of the system. So that's a different type of machine learning called deep reinforcement learning that most people have heard about in the recent past with respect to the game-playing AIs from DeepMind. So AlphaZero, AlphaGo, AlphaStar, these systems who train AIs to play games, that system, we have applied that to this particular model as well, to create an adaptive, personalized approach to controlling sepsis.
Okay, and so the generalizable algorithm, it's sort of an initial conditions or an initial model, and that could take reinforcements back. It could improve over time, and it can adapt to the individual it's being applied to.
So the GA was just a concept demonstration to say that the system could theoretically be controlled to some degree. In its current form, the GA is not directly related to the deep reinforcement learning process, though we have more exotic combined approaches to deal with some of the model improvement aspects.
When you go into the machine learning world, though, that implies that you're using historical data to sort of predict or cluster patients, right? So how does that fit with sort of the ABM?
Right. So at this point in time,
mechanics?
we need to make a distinction between model-based DRL and non-model-based DRL. Right. So the game playing AIs are model-based deep reinforcement learning. And the way that those systems work is they have essentially computational representation of the game, and they essentially fill out the possibility and trajectory space of that particular problem with enough density so that effective probabilistic decision trees can be made. Right. So Most people do not do model-based DRL in the medical area, and what they try and do is they try and use prior data to construct, these decision trees based on available data. So one of the more commonly popularized ones is the DRL AI trained for the virtual clinician for sepsis management. Now that one, that model is a model-free DRL, and its control space, right? The control space that the AI has is essentially pressors and fluids. So it can, decide based on, historical data, which one of things that should be done. There are, problems with that because it cannot actually generate novel counterfactuals for what happens if you don't do something. So the penalties for the for the decisions are not objective, let me put it that way. But it can't try anything new. So if you do model-free DRL, what you described is exactly the problem, is that you can't actually test a new therapy. You can't actually try something that hasn't already been implemented in the clinic and actually been, run at scale, had lots of people who've gotten it. So alternatively, our model-based DRL is much more similar to the DeepMind projects in so much that the IRABM, the agent-based model, is that instantiation. It is the model upon which the AI agent learns. So it will run, millions or billions of potential trajectories and manipulate the system, in that particular fashion to come up with a policy embedded within the AI that controls that particular system.
Okay. Gary, we'll take a quick break. When we come back, we'll talk more about, you have another paper in the area of sepsis, and then we talk a bit about the crisis in reproducibility paper as well.
All right.
Okay. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. So Gary, we were talking about sepsis before the break and some of the agent-based modeling that you do, genetic algorithms, machine learning techniques. You have another more recent paper in the area of sepsis entitled Sepsis Reconsidered, Identifying Novel Metrics for Behavioral Landscape Characterization with a High-Performance Computing Implementation of an agent-based model. Again, sepsis, as you say here, affects 1 million people in the US per year, very high mortality, up to 50%, and requires more than 20 billion a year in hospital costs. So it's a big problem. And as you describe, it is not very highly defined. It is very heterogeneous, so it's often difficult to precisely treat. And so it's very amenable to these types of mathematical modeling. You want to talk about a bit about what this high-performance computing platform does in the ABM context?
Sure. So, high-performance computing is supercomputing to most people. And the idea here is that you can generate simulated populations at much greater scale than are possibly clinically possible. And the reason you want to do this is because of the heterogeneity that you previously mentioned. There is a vast gap between the definition of sepsis and the definition of severity of illness, which is very much characterized at the organ level phenotype, organ dysfunction level phenotype, from the cellular and molecular knowledge that we have about this system, cytokines, cell populations, etc. Right. So people have tried to use very rough types of characterization of groups of patients suffering from sepsis based on biomarker panels, gene expression data, transcriptome data, these types of things, but I think the challenge is that it is a moving target, as alluded to in the prior section, that a patient on day 1 is not the same patient as that patient on day 5, right? And may require something different.
Yeah, so for my own understanding, Gary, so sepsis is a condition, right? So you can get there from variety of disease states,
Yep.
right? And so that's the issue. So you could get there from a lot of different initial conditions, and as you say, once it has different stages. And is it as diverse as cancer, that anybody's sepsis is different from anybody else's sepsis, how it progresses?
Probably not quite as diverse as cancer, given the various types of ways that tumors can behave, but it is clearly very heterogeneous. To take your example one step deeper, people who have certain types of medical comorbidities like diabetes, obesity, smoking, cardiac disease, etc., have differential responsiveness to systemic insult, and therefore they respond in a different fashion. So this paper that we're talking about now is an attempt to essentially map out the landscape of all the possibilities that are there with respect to trajectories of systems through cytokine space. What I mean by cytokine space is, if you imagine every single mediator that you could measure, it represents a different axis in this multidimensional conceptual space that an individual patient will pass through as they go through their course of disease. Right.
So if you have the predictability, if you have early intervention, is that a condition you can avoid?
It turns out that this paper suggests that that's not possible, right? And part of the reason for this paper is to, as I alluded to with the neuroscientist and microprocessor paper, is to say, don't do this thing because it's not going to work, and we can prove that it's not going to work using a proxy system. So what we set out to demonstrate is, with a model for which we have ground truth, there are no hidden variables, and there is we can sample it every single time step, right? So there's no issue with respect to data density. So let me step back for a second. The invariable, let's call it excuse, for the failure of predictive biomarker panels is that there isn't enough data, or they need more data. Right. Now that's a path to infinite regress, because you can always ask for more data. Right. You can always ask for more data.
Yeah.
So what this project was focused on is say, okay, we will have a system which we recognize is vastly simpler than the immune system, vastly simpler. But it's pretty complex and reproduces the main dynamics associated with sepsis. And we will there is no data paucity there. This is where the supercomputing component comes in. Because we run these simulations on a supercomputer, there is no limit to the amount of data that you can have. And therefore, you can have complete state identification of the system at every single time step possible. So every 6 minutes across this multidimensional cytokine space for 90 days. I mean, that is a lot of data. And once you get that data, you want to say, can you predict, based on any sort of biomarker panel that you come up with, whether or not that system is going to live or die? And you cannot. It turns out that there is no, and I make the qualification, there is no linear combinatorial biomarker panel that can predict outcome for this system.
So you say here that it examined by simulating over 70 million sepsis patients for up to 90 days. So this is simulating patients and patient behavior. So presumably you have a set of heuristics there, or set of rules there.
Well, it's the IRABM, the model we talked about previously.
The model you talked about. Okay.
Right.
Okay.
And the key here is that a quote unquote simulated patient isn't like a complete organ, containing individual. A simulated patient is one run of that particular agent-based model.
Right. Okay. But the data being generated obviously is dependent on what you have in the model, though, right? So ultimately, what is being tested here?
What is being tested is whether this approach of looking for a biomarker panel for
it's
not viable. It doesn't. There is no. There is no way that system will work, because we have taken away the complaint or the excuse that we don't have enough data and we don't have enough temporally rich data. And this is for a system that is much simpler than the real world. Right. So if you can't even do it for a simplified version of the real world system, the model is complex, but it's orders of magnitude less complex than the real human system. So even with a simplified system for which you have ground truth, for which there is no limitation on the data that you can acquire, if you use standard attempts to construct predictive biomarker panels, you will not get areas under the receiving operating curve better than about 70%, which is essentially a guess.
Okay. And so just to repeat that for my own understanding, so if you put into sort of a simulation of a simple model in this area, and do that, for a large number of trials, and look at predictability of a patient progressing into sepsis, even with that simple model, there isn't enough predictability. So you argue, if you really look at real systems, real patients, your ability to predict if that patient is going to go into sepsis or progress into worse conditions is close to zero.
Using traditional methods.
Traditional methods.
So the novel metrics that are alluded to in the title of this particular paper are the construction of these things called probabilistic basins of attraction and stochastic trajectory analysis graphs that do give you additional insight into what the possible outcome of a particular configuration is based on their particular position in cytokine space. So if you think about, and this I think is a really important concept, is that biological systems are probabilistic systems, that they deal with inherent uncertainties associated with them. So an analogy that you can use, which is a very rough analogy, is that these probabilistic basins of attractions are not completely different from the idea of electron shells as probability distributions in quantum mechanics, where the position of an electron follows some topological probability distribution based on features associated with its charge, etc. And similarly, we can construct these probability clouds of where individuals may or may not be based on their position in multidimensional cytokine space.
So have you shown that such a process has a high level of predictability?
Well, it shows that you cannot predict with any.
Oh, it's still, so you still cannot
Well,
predict.
I mean,
Okay.
so what you can do is you can get probabilities, but if your
Yeah.
probabilities are poor, right, then
Right.
you can't predict. So you can find outliers where you have a 90%, 95% chance, 99% chance of either living or dying. But those are almost trivial cases because those are readily identifiable clinically. The tricky parts are the ones where the probability distribution is about 50%. And there's a vast region in cytokine space where this is a problem. So we have, not to keep taking tangents, but we've actually addressed this to a certain degree by training an artificial neural network to function as a predictor or a forecaster for the behavior of this particular system, not too dissimilar from how the Weather Service uses mathematical models to predict the future trajectory of a hurricane. Similar to that particular process, the uncertainty is due to a different issue, but you have this essentially forecasting cone that, given a particular set of data and a particular position, we can give you a probability distribution moving forward, 30 minutes, 1 hour, 6 hours, 12 hours, about where that system is going to be. And then you need to update that system with new data to reset what that cone is. So we have more recent work that uses machine learning to train artificial neural network to do this. And this, I think, is kind of the future of predictive analytics, because you're going to need that density of trajectory coverage to be able to do any sort of meaningful prediction if you're looking at biomarker data.
Right. So in a practical context, then does it have value in designing an intervention?
At this point, it doesn't exactly do that, though. Combining it with the DRL work we discussed earlier, eventually, I mean, it's my contention, it's the only way that you can do it, right? Because that's how control systems in every other field of technology function, that they have a underlying mathematical model or data model, if it's simple enough, that is operated upon by a trained system, be it an expert system or a neural network. So I think in the future, I think it has to be this way, because you can't actually get that sort of density of possibilities from the real world. So there are probably maybe 20,000 patients, septic patients, for which there exists data in all of human history, right? That's a fraction of the 70 million that we simulated. And you aren't going to be able to fill out that multidimensional trajectory space using clinical data. It's impossible.
Yeah, it's, without knowing a lot about it, my feeling is that these biological systems are chaotic systems, and you alluded to it, they could be quantum mechanical. And so our attempts to really understand it more from a component basis have always failed. So R&D processes, and I think you talked about this too, there is very little correlation between animal models and human models, but we go through this feel-good exercises in pharma R&D as if that is a very useful thing. But ultimately, it doesn't really increase lot of understanding, right, of how human systems ultimately react to it, right?
Yeah. So I think it's easy to be very hard on the pharmaceutical or the biomedical research community, but they're not at fault because they don't have anything else, right? Right. So these reductionist methods are necessary because you can't figure out in any other way how something actually works. So there's a synthesis part of this that's missing. So if you don't mind, I will take this opportunity to jump into that Crisis of Reproducibility paper, because it is directly related to this issue. Right. So for those of the listeners who don't know what the crisis of reproducibility is that in multiple biologically related fields, some of the seminal papers that form the basis of, multiple billions of dollars of drug design cannot be reproduced by other laboratories, right? So it calls to question this kind of epistemic crisis of what is actually known and how much can we trust what we actually know. Now, if you're a basic scientist, you know this intimately, because if you have a particular experimental system, highly engineered and calibrated to your particular setting, every time you get a new postdoc, every time you change the species of your mice, every time you change the feed, that model breaks, right? That model is very, very brittle. And that must cause you, it should cause you to question how reliable is the knowledge that I extract from this particular experimental platform if it breaks when I do what are essentially trivial things to the real world, environment of disease. So that the challenge that biomedicine has is it has no way of deciding what is similar between this system and this other system, right? They do it in a very kind of descriptive sort of way, but it isn't rigorous. It's not objective, right? So when you take a mouse, right, and you do something to it, and then you say, okay, what is the essential mouseness of this particular representation of what we think is happening? That would allow me to say what is going on in this mouse is similar to this other mouse, right? So we want to be able to have some mechanism of conserving what is similar when we look at it in different types of, let's call them trajectories. So this goes back to the idea of multiple trajectories from similar rules that is at the core of agent-based modeling, where you can have exactly the same sorts of rules, but you can have multiple different behavioral trajectories based on all sorts of individual perturbations, right, that occur to that particular object over time. So my contention.
Yes.
Go ahead. I'll let you.
No, I was just going to say, so again, for my own understanding, so the biomedical research, as you mentioned, because the systems that they're attempting to manipulate, to influence are so complex, they just do the experiments, they just look at the data, and what you're saying is that the reproducibility of those experiments are not very high. If I understand you correctly, Gary, what you're saying is that you can abstract that mathematically. If you can abstract that mathematically, then perhaps you can improve the reproducibility of the experiment.
Right. So let's take out the example of bad data. Right. So let's assume that there's no measurement error, but you have two different mouse experiments that are performed by different postdocs, and you get two sets of data that are very different. Now, you don't have measurement error. Now, you haven't done the right protocol or something like that, but the fact is that mouse is able to produce that data. Whatever it is you did to it, you're able to generate that particular data, right? So, and this is one of the novel parts of this idea, is that you actually want very messy data. You want data that's got a very wide spread, because in order to hit those particular data points, right, you need that heterogeneity of data serves as a constraint on whether or not you can find a configuration of your underlying hypothesis structure or model that can achieve those sorts of things. So why is this important? This is important because every scientist recognizes that mice are not humans. Everybody knows this, right? I mean, it's like trivial, and yet people constantly say, "Oh, it worked in mice, and therefore has promise in humans." It's that particular step, right? There is no there's no way to do useful failure if you don't have any sort of object that can be refined through that particular translational process.
Yeah, so we use this term mouse model, right? Again, correct me if I'm wrong. What you're saying is that there is no model unless you can show some sort of mathematical computational model of what the experiment is. Because when we say it's a mouse model, there are a set of assumptions that go around it. And like you say, we can now take it to human. We expect certain toxicity and certain efficacy, but you often don't find any of those, right? The correlations there are very, 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 very low. And so are you saying, Gary, that there is no mouse model unless you can show a mathematical representation of it?
I think saying no model is a little bit, too encompassing, because model is a very, generic term. So clearly, that model can be implied. Yeah. But I think what is missing is a consistent representation of what it is that you're saying is happening in that mouse that is now also happening in that human being. Right. So as a mammal, a mouse has very many of the same cellular features associated with the inflammatory response. Now we know that the mouse inflammatory system behaves very differently than the human system, but the core components of that system as a mammal are shared. So my contention is that the variance between those two organisms can be reflected as in the parameters that are associated with the model, right? Because that essentially affects the gain and the strength of the interactions that are present, which very often is the result of genetic variability, right, or epigenetic variability.
Right. And if there is a process of scaling it and scoping it, then even before running the experiment in a scaled up and scoped up system, you will have certain expectations.
That's right. You would have some way to anticipate, based on your prior experience of using the model as this translational object, to say whether or not I have a reasonable expectation that this intervention is or is not going to work.
Right. And so this has applications to both sort of reducing the number of experiments that need to be run and or increasing the success rates potentially, right?
Exactly.
Of the process.
And is absolutely essential if you're going to do personalized medicine, because the same principle applies to clinical interpatient heterogeneity, because we're all human beings. The wiring is all the same, right? The parameters by which we respond are slightly different, right? Based on our genetic makeup, comorbidities, et cetera, right? So if you're trying to reproduce the heterogeneity of the clinical population, you need this grounding of the computational object upon which you now layer the various aspects of parameter space. And that's discussed in this the Sepsis Reconsidered paper as well. The concept of parameter space as a representation of interpatient heterogeneity.
Okay. So this is a very interesting research area, Gary. So in conclusion, if you look forward 5 years, clearly, the computational capabilities are increasing almost exponentially. We can solve very complex problems now. There's problems we couldn't even think of solving just 5 years ago. So if you look forward 5 years, where do you think this type of an idea would go? And from your perspective, where might it have the highest applicability?
Well, I have to say that I've been very discouraged over my 20 years of working on this. Because when I started with this, I thought, well, of course, this makes perfect sense, and that's not how the scientific community works. So my hope is that there is some generalized realization of the importance of dealing with partial knowledge or uncertainty. And this is a whole nother topic, right? But the idea that a partially okay model is very useful is important. I'm not going to say the George Box quote, which I absolutely despise, but the idea is that a very useful model can be obtained from something that's not a complete representation of the system that you're dealing with. I think what's necessary from my standpoint is a concrete use case demonstration that this works, right? That the use of a agent-based model as a proxy system for which you design a controller and then you have the ability to execute that control in the real has a demonstrated efficacy in improving a individual's outcome. That is the thing that we're striving for. Whether we can do that in 5 years, I'm not sure, but that is the hope.
Yeah, and the difficulty there obviously is you have to show that you're beating a human, right? That's your competition, and the human comes with a lot of intuition, experience, and even information that the human can't really describe but exist in his or her brain, right? So that is where the contention is going to be. Can we demonstrably show superiority to a human? Or it's not something
that's actually not the problem, because I'm not competing with a clinician. I'm competing with the pharmaceutical industry.
Yeah.
Right. So the pharmaceutical industry has a failure rate of 99.999%. Right. And we have diseases like sepsis for which there is no approved therapy. So coming up with anything that works is going to be a win.
Right. And it's, 20 years ago when I was doing this, it took a drug from idea to market about $1.4 billion to get to market. With inflation and everything, it's about 1.8 billion, adjusted for attrition, of course. And so there's a lot of economics there, even if you can show some slight improvement.
Yeah, and I think, I showed this graph. It's from several years ago that shows efficacy in drugs to market based on expenditures, and it did not look good. Now that graph is reversed in the last 4 to 5 years, but it's because the goalposts have been moved in terms of what is considered to be acceptable for a drug. This is primarily cancer. So again, a different topic, but I think the fundamental scientific challenge persists.
Right. Excellent. Yeah, this has been great, Gary. Thanks so much for spending time with me, and good luck with these ideas. I think it's really.
All right. Thank you very much for the invite, and it's been a pleasure speaking with you. Okay.
Thank you.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.